the key to separation of variables is these eigenvalue problems that come up for the x-dependent part of the solution. That's going to involve the boundary conditions that you have in your original PDE. Okay, and so for separation of variables, right? I'll just say now this is in general. Sorry, my screen's doing something weird. Not letting me write there. We're going to get this kind of class of eigenvalue problems that are going to give us the eigenvalues and the eigenfunctions that are going to determine the behavior of our solution. And the problem that we kind of set up and worked partially through on Friday, you know, talked about another situation where you have, you know, maybe mixed boundary conditions that preclude you having a nice, straightforward, explicit solution to that eigenvalue problem, which is possible. But you can still learn something about the kinds of solutions you'll get and whether you're going to get, let's say, positive or negative eigenvalues, which will potentially determine the behavior of your solution. Okay? And so separation of variables in general, right? As we say, it leads to a large class of eigenvalue problems, okay? And so we'd like to gain some intuition on them, okay? So we will study, okay, what's called their L2 theory. And L2 theory really means how do these solutions behave with respect to the L2 norm, right? So the L2 norm, right, of f is just going to be the square root of the integral over whatever space that that function lives in, f of x squared dx square root, right? So because we're shrouding these functions in an integral now, okay, problems like, you know, continuity are not as big of an issue here because we can have, you know, piecewise discontinuities, we can have holes in these functions, and we really just want to measure, you know, how well these separated variable solutions do in terms of the L2 norm. Why? Well, because it's kind of an easier theory to build up. And if you're building something like numerical spectral methods for solving these equations, that's usually good enough, and they'll have nice smoothing properties because usually your eigenfunctions are smooth even if your actual solutions are not, okay? Or you know, your solutions to the original PDE are not, right? So so what are we going to look for? So we're going to look for completeness and orthogonality, okay, of eigenfunctions, okay, in the L2 inner product, okay, and we're going to talk more about that, but essentially that's the machinery that we're going to work with, okay. So just to jump right into it, okay, I'm going to write down kind of the general eigenvalue problem that you get by studying any number of second order linear PDEs. They could have variable coefficients, right? And so if the eigenfunction is V, then a typical Sturm-Liouville problem looks like this, right? Where lambda is the eigenvalue, x is going to live on A to B, p of x is going to be a positive function on A to B, the open interval, okay? And we're going to need some linear homogeneous BCs at x equals AB, okay? In the lecture last week, we talked about if you have inhomogeneous boundary conditions, then essentially the way you get around this is that you really just solve the homogeneous problem. And you can essentially make the limit of your solution equal to the boundary condition, and then you'll just have this essentially this jump discontinuity where all of the eigenfunctions maybe are 0 on the boundary, okay, but you have this limiting behavior that looks like it should, okay. And we talked about how to do that in the case of the inhomogeneous heat equation. I think of the recorded lecture last week, okay? So note that the case P is equivalently 1, Q is equivalently 0, and R is equivalently 1, okay, corresponds to our previous eigenvalue problems, right, that we got in the context of the heat equation with Dirichlet boundary conditions. Okay, and rather than continually writing this, right, we can just define this as a linear operator, okay, and then use theory of linear operators. So let's define the differential operator, okay, we'll call it curly L, by L acting on some function b of x is equal to minus ddx, p of x, dv dx, plus q of x, v of x. Okay, so just the left-hand side of this equation up here. Okay, so generally what we want is that L should take in what? Well, we need some regularity conditions on V. What do you think those should be? For our eigenfunctions. Can V be any old function?
Differentiable?
Yeah, so twice differentiable, right? Because we got a derivative out here and a derivative here, right? So let's make it C2, let's say on the closed interval from A to B. And it's going to return, some right-hand side, which may only need to be continuous on A to B, okay? So then LV is equal to lambda RV. Okay, so that's our eigenvalue, okay? Not only do we need this though, right? But we also need what? Well, if we're dealing with our eigenvalue problem, we probably want to restrict our set of functions that we're worried about to the functions that satisfy these linear homogeneous boundary conditions, okay? So if we restrict the domain of L to just be, C2 functions with the boundary conditions that we need, then we're living in the, space of potential functions that should, well, at least get us in the direction of getting eigenfunction solutions to this problem here. Okay, so if we restrict the domain of L, okay, to let's see, C2AB functions, okay, and boundary conditions satisfied, okay, then for instance, we could have a number of requirements on V, right? So if we remember from last time, right, we had Dirichlet boundary conditions. These were like that V of A equals 0 equals V of B, okay? We could have Neumann boundary conditions, okay? where the first derivative, the first spatial derivative here is equal to 0. These are sometimes called no flux boundary conditions, but it actually depends on the linear operator that you have, actually what the flux is. But if it's the heat equation or the diffusion equation, then yeah, these would be called no flux conditions. Okay. You could have periodic boundary conditions, and these would be considered homogeneous boundary conditions. What's a periodic boundary condition? Well, that's essentially that V of A is equal to V of B. So the idea here is that, maybe you're modeling, heat conduction in some annulus or something like that. And here's like X equals A, and then you go all the way around. And then here's X equals B at this end, right? Or you could have periodic flux boundary condition. So V prime of A equals V prime of B, okay? Or as we talked about some on Friday, you could have what are called Robin boundary conditions, where you have V prime of 0 minus some scaling, V prime of A, alpha A, I guess I'll call it, V of A is equal to 0, V prime of B plus alpha B, V of B is equal to 0. So sometimes these are called, partially absorbing boundary conditions. You could also have mixed boundary conditions, which would be like, V of A equals 0, while V prime of B plus alpha B, V of B equals 0. So you have a Dirichlet on the left end and a Robin on the right end, or you could have, Dirichlet on the left end and then Neumann on the right end. So you have, absorbing on one end and no flux on the other end. And these could be physically motivated, for your particular problem. And in general, you might expect to encounter problems where you're going to have these mixed boundary conditions. Okay.
Professor,
Yeah.
for periodic boundary conditions, both Dirichlet and Neumann conditions should be satisfied, right? Compulsorily.
Yeah.
But not 0.
Right. So if you're really dealing with a periodic domain, then you're going to expect to have those together. If you want to have like a C2 function. I'm trying to think if there's some strange situation where you might have a periodic boundary condition plus some other condition. I mean, you could probably cook up PDEs where you would have a combination of periodic and other boundary conditions. But yeah, you expect those to come together usually. Certainly they will in this class. Yeah. So generally, we can represent these, again, just like as some operator. So call it B acting on V equals 0, right? So like, e.g. BV might equal something like V of A and V of B, right? This is like your linear, that's a linear operator, okay? All right. So fine. So now we have this way of kind of representing these problems more generally, right? Well, like we don't have to just deal with kind of a nicely behaved heat equation example. This could come from any number of PDEs. Okay. So let's start doing some work on this differential operator. So let's consider the differential operator, okay? L is equal to, you know what, I have all the sheets I want, so I'm not gonna, I should just start on a new slide, sorry about this. You can still write down what you were writing down before. Okay, so let's consider the differential operator L is equal to, right, minus d dx, p of x, d dx, plus q of x. So now I've just sort of written that differential operator by itself, okay? And the L2 inner product, as promised before, right? And this is going to be what, okay? The inner product of u with v, right? The analog of sort of vectors is that we integrate them against each other. So u of x and v conjugate of x dx, right? Although we're primarily going to be working with real functions here, is defined so long as u and v are C2 and, well, we define them for u and v being C2 and a and b, okay? All right. Although that still works even if they don't have those continuity properties, right? So here's a question then. What is the condition on u and v such that LUV is equal to U LV? In other words, that the operator is what's called self-adjoint, right? And if you remember back to linear algebra, right, when you're dealing with matrices, if you have symmetric matrices, you can say a lot of nice things about their eigenvalues, right? We're in the same situation here, but instead of a matrix being our linear operator, we just have a differential operator as well, okay? So we'd like to see if we can prove something general about operators that come out of Sturm-Liouville theory so that we can make general comments about their eigenvalues, so that maybe we can make general statements about their eigenfunctions, so that we can then say something about whether or not solutions to Sturm-Liouville problems provide us with these nice, complete orthogonal sets that we can use to make solutions to PDEs, okay? So that's why we want to do this, okay? So fine, so how do we do this? Well, we just charge ahead. We just see what happens if we compute this L2 inner product. As you might imagine, we're going to use integration by parts to try and massage the L2 inner product into something that looks like this. So we're going to get conditions that ensure that that's true. Okay, so let's do it. So let's start by saying, right, LUV is equal to, well, let's just compute the L2 inner product, right? So we get minus P of x, and I'm just going to use primes in this case. So U prime plus Q of x, U, and then I have a V conjugate here, x dx, right? If I integrate by parts, okay, I'm left with boundary terms, which are minus P U prime V conjugate evaluated between x equals a and x equals b, plus the integral from a to b of p of x u prime v conjugate prime plus q of x u v conjugate dx, right? Integrate by parts again, and I'm starting to pile up terms in my boundary terms here. So now I'm going to add on u p v conjugate prime evaluated between x equals a and b, plus this integral now, the integral from a to b of u times q of x v conjugate minus P V conjugate prime prime and integrated with respect to dx. Okay? So now I'm going to assume that P and Q are real functions, okay? So that I can sort of pass this conjugate through essentially, so that it won't affect things. And I can rearrange my boundary terms a bit. And I end up with P U V conjugate prime minus U prime V conjugate evaluated between x equals A and x equals B. Plus now, if we look at this, right, this is really just U's inner product with L acting on V, but the conjugate of that, right? And because we're assuming these are real, then they won't be affected by the conjugate, okay? So I can just write this whole thing like U inner product with LV, okay? So everything's fine, right? This is equal to this, but now plus this, right? But remember that we have homogeneous boundary conditions, okay? So what's our condition that we need to satisfy now? Well, we just need that this thing is 0, okay? When is this thing going to be 0? Is it going to be 0 for all the boundary conditions that we listed? Okay, so if P U V conjugate minus U prime V conjugate x equals A, x equals B equals 0, right? Then L is self-adjoint, okay? So what do we need to do? Well, we need to check our boundary conditions, okay? And some of these will be left as an exercise to you. You know, one thing you can probably see immediately is that if U and V are both like, you know, Dirichlet boundaries, then this works. If V and U both have Neumann boundaries, right, then this works, right? So you're allowed to have V inherit the boundary conditions of U, right, and vice versa, okay? So you can check the boundary conditions, but essentially this condition will be satisfied, this thing right here that I've written down, right? Will work for homogeneous Dirichlet, homogeneous Neumann, okay? Homogeneous Robin boundary conditions, that's a bit more work, okay? Periodic boundary conditions, right? So all the ones that we wrote down on the previous page, okay? So you'll have a chance to prove that in your homework that I'll assign on Wednesday, okay? So questions about this?
So for inhomogeneous, say, Dirichlet boundary conditions, we would plug those in and get some different conditions on the derivatives.
Right, yeah. So if we were dealing with like a non-homogeneous eigenvalue problem, exactly, right? This condition here would essentially give you a condition that would tell you, you know, how the boundary conditions should be inherited by the adjoint in order for your linear operator to be adjoint, right, or self-adjoint.